Alright guys, welcome to the first episode of GGTutoring. I'm one of your co-hosts, Varun. I have another buddy, his name is Will. He does the other portion of this tutoring services. So my role in GGTutoring is I focus on Bio 151 and Chem 343. My other co-host, Will, he'll also do some Chem 343 and he'll also do some genetics. So for all you students at UW-Madison, GGTutoring is the best service here on campus. Free tutoring services. GG, good game. You know, you take that exam, it's wraps, bro. Like, it's easy. Once you learn from us, that test is GG, bro. Like, you're in good hands with GGTutoring, all right? So, for a lot of you folks, I know you guys are probably struggling with Chem 343 right now. So, I got you, okay? So, I know exam 1's already over, right? So, we got to focus on exam 2, right? So, we got to lock in now with GGTutoring. So one of the hardest concepts is stereochemistry, right? It's very hard to visualize the stereochemistry on paper, but I'm going to make it much more simpler for you guys today with some drawn explanations and some 3D models, okay? So let's dive right in. All right, guys, so we're going to start off by just kind of explaining how to assign stereocenters of molecules, right? So you can either be an R or you can be an S for like a stereocenter. But to do this first, you need to have a chiral stereocenter first. So what does it mean to be a chiral center, right? So I've drawn this molecule right here. Carbon attached to hydrogen, carbon attached to a fluorine, a carbon attached to an OH group, and a carbon attached to a CH3 group. So this carbon right here, it's attached to 4 different groups. You see that the F, the H, the OH, and the CH3 are all different groups. So because it's attached to 4 different groups, that means it's a chiral center, right? But I'll draw an example of an achiral center. Let's say you have this carbon attached to a OH, an H, another CH3, and another CH3. You can see that these 2 groups that I've underlined are exactly the same group, and this therefore makes the carbon an achiral center, because it doesn't have 4 different groups attached to the main carbon in the middle. It doesn't have to be just carbon that can be a chiral center. It could be any other atom or molecule. It doesn't really matter. But as long as it's attached to 4 different groups, you can call it a chiral center, okay? But you can see that this molecule right here that I've drawn earlier, if you do it in its mirror image, I was just drawing this green line as a mirror, and if I were to draw this mirror image, it would still be the OH is coming out into the top. The CH3 is coming out in the same plane. And you still have the fluorine coming out as a dash. And you still have the H going back into the plane. But because even though that you reflected over its mirror image, it's non-superimposable, because if you try to rotate the molecule and put it back over itself, it's not going to fit exactly how it would be. And therefore, these are considered to be enantiomers of each other. Because they are non-superimposable, even though they have the exact same molecule, they have the same connectivities, its spatial arrangement, it makes them different. Because if you try and rotate the molecule on the right by 180 degrees and put it back onto itself on the left molecule, it's not going to line up identically. And so therefore, they are enantiomers. So to take this step a little bit further, right, we can also kind of differentiate them to see how they're kind of different molecules by assigning R or S to them. So by doing that, we need to assign priorities to these different 4 groups that are shown connected to the carbon. The way by doing that is taking it atom by atom. You don't want to assign priority just by looking, it's an OH group or it's a CH3. You want to go atom by atom. And by using your periodic table, you can also kind of determine which one has higher priority. Most of the time, H is going to be the lowest priority group because it's like the smallest molecule. But you're basically assigning this based off like atomic size and its mass. Fluorine on the periodic table has its biggest mass in these 4 molecules I've drawn. So we can say that fluorine is 1. It's like our main priority group. And then oxygen would be 2. And then carbon would be 3. and then H would be 4. But sometimes it can be a little bit more ambiguous, so I'll draw another example. So let's say that we have a carbon attached to an OH, attached to a hydrogen, attached to a fluorine, no, I'll change this, attached to a CH3, or CH2, CH3, and attached to a CH3. So how do we determine the priority of these groups? So we would say that our oxygen is the highest because it has the highest atomic mass. So it would be our 1. Hydrogen most likely be 4, right? But now we come across 2 carbons, and we could say those are pretty much equal, right? So now we have to go to the next point of difference to determine which would be higher priority. So we know that this main carbon is connected to a carbon, and that carbon is connected to 3 hydrogens. For the other group, this main carbon is connected to a carbon, but it's connected to 2 hydrogens and a carbon. So we can kind of do a process of elimination, right? They both have 2 hydrogens that the second carbon is attached to, but the point of difference arises from this H and this carbon. And as we know, carbon is a higher priority than H. So we could assign this group as our second priority, and this one as our third priority, right? So now that we have our priorities assigned, we can kind of basically figure out whether or not it's an R or S configuration. And the easiest way to kind of figure this out is the lowest priority group should always be going out of into the plane. It should be on a dash. So you see how our hydrogen right here is circled. It's a dash and not a wedge. So that's already a good thing. It made it a lot easier for us. And basically the way to determine if it's R or S, if your priority groups are going clockwise, it'd be R. And if your priority groups are going counterclockwise, it'd be S. So on the left side of the mirror, we can see that our hydrogen's already going into the plane, which is good for us. We don't really have to change anything. So we see that our fluorine is 1, our OH is 2, and our CH3 is 3, is our third priority group. And just following the numbers, we can see that it's going in a counterclockwise direction, and therefore it would be an S conformation. Now we can kind of see that on our right side, the hydrogen is going into the plane, which is good. And so it'd be our 4. So I'll just reassign priorities. F is 1, oxygen is 2, and carbon is 3. And we already see that the hydrogen is going into the plane, which is a good thing, so we don't have to change anything. And then following the numbers of the priorities, it's going in a clockwise direction, and this would be our R. So that's kind of the basics to assigning priorities and how to determine what groups are your highest priorities and assigning R and S configuration. Alright guys, so I've drawn a new example, right? So you see as above, our hydrogen earlier was going out of the plane, or into the plane, sorry. But now in this example, our highest priority group, fluorine, is going into the plane, and our lowest priority group, our hydrogen, is going out of the plane. So how would we assign priority to this molecule? Well, based off what I've taught you guys already, we would assume that going in the direction of our highest priority groups, you'd go this direction. And since it's counterclockwise, you'd assign it S, right? Well, we can't really do that because our hydrogen, our lowest priority group, is not going into the plane, right? So we can assume this is wrong. So the way to make this process easier to assign configuration is by kind of redrawing this molecule and just saying that the H is going into the plane and F is going out of the plane just by switching them, right? So I'll redraw it, and we got the C going to the OH as like last time, our CH3 group. Now we'll draw, sorry guys. Then I'll draw our wedge of fluorine going out of the plane and our hydrogen going into the plane. So I basically just switched these two groups around to determine whether they're going into or out of the plane. And based off our priorities, fluorine 1, oxygen 2, carbon 3, and hydrogen 4, we now see our hydrogens going into the plane, and we know that following this direction, it's S, correct? Because S, as I said before, is counterclockwise. So now, basically, we see that an original molecule, now that we flipped it, it was S. So basically the way of figuring out the conformation, the S or R, is basically just taking the inverse of what you changed and assign it. So when I changed the F and H around, we determined that was S. So that means when we reverse it again back to its original, you're just taking the inverse, or you're just flipping the S to an R. So this would now become an R conformation, if that makes sense. So that's basically just like the basics of assigning highest priority to different groups and determining if it's S or R. Alright guys, so now we're on to the visual representation, just to make this more clear for you guys if you guys have not understood yet. So I made the same molecule I was talking about before with our chiral carbon right here, attached to a CH group right here, an OH group up here, a hydrogen right here, and a fluorine right here. And I made this mirror image, pretend that in between these two molecules is a mirror plane. So they're mirror images of each other, right? You can see how in the mirror image that these fluorines match up with each other, the hydrogens match up to each other, the OH groups match up to each other, and the CH groups are equally distanced. So when I was talking about non-superimposability, so let's say that we rotate this mirror reflection 180 degrees to try and superimpose it. You do this, you flip it, and you try and match it up with this molecule. You can see how these two CH groups kind of match up, but the OH groups are going in opposite directions. And you can see how this fluorine right here matches up with this hydrogen, and the other side, it's the same thing. So they don't line up exactly the same way, because for it to be imposable, all the molecules would line up. So there would be a fluorine here, but there's a hydrogen here. You see how they don't really add up together. So they're non-superimposable, even though they are the same molecule, but the spatial connectivities are different. So if you guys are having trouble understanding this on paper when you're seeing different questions, try and build a model kit, because it can help you visualize a lot better, okay? So the same thing kind of goes when assigning priorities, right? You have your chiral center, you have your OH, your fluorine, CH3 group, and your hydrogen. So we kind of want to put the hydrogen, a large priority group, back into the plane. So when you're kind of visualizing, as you can kind of see from where I'm looking from, you have your 1, 2, and 3. Because it's going counterclockwise, right? It's S. And then for the mirror image molecule, we were talking about later, you have your 1, 2, 3, and it goes clockwise direction, so it's R. I hope I was able to share some knowledge with you guys. You guys can pick up on it as well. So if you have any other questions, feel free to drop some questions in the comments down below. I don't know, if you're in my lecture, try and find me. I'll help you out, because that's what GGTutoring is all about, okay? So that kind of wraps up for this episode. I mean, I'll be posting more episodes soon, but this is just kind of the introduction to our channel, just getting out a basic video. I'll be posting more videos as the semester goes along, as we get closer to our exams, so stay tuned for that. My other co-tutor, Will, he'll be on the channel eventually doing his portion, whatever he does, so stay tuned for that. And I hope this is a good lesson for you guys, and stay tuned, guys. Thank you so much. I appreciate y'all. GG Tutoring is the best on campus.